A very good evening to all of you. Thank you for joining us today as we dive into the future of space exploration with our exciting Thrust Talk webinar hosted by the Rocketry division of SEDS OUSL. I'm Sarah Rafik, and alongside me is my dynamic co host for the evening, Sharindu Lakshan. We are absolutely thrilled to have you here for what promises to be an inspiring look into the future of space travel. As you know, space exploration is rapidly evolving, and rocket engines are at the heart of this progress. We are pushing the limits of technology to explore deep space, colonize other planets, and uncover the mysteries of our universe, and that's why today's topic is so important. And tonight, we are honored to have Dr. Janit Veerasinghe, a renowned expert in space propulsion systems, as our guest speaker.
So, once again, thank you all for being here. Before we dive in and to officially kick things off, I invite the Assistant Manager of the Rocketry Division of the SETS chapter of the Open University of Sri Lanka, Medini Hansika, to deliver the welcome speech.
Good evening, everyone, and a warm welcome to Trust Talk, Rocket Engines and their powering of the future of space exploration. On behalf of the Rocketry Division of SEDSA USL, I am honored to welcome all of you to this exciting and insightful webinar. Today, we will explore one of the most fascinating topics in aerospace engineering, the design and power of rocket engines that are shaping the future of space exploration. It's my pleasure to welcome our keynote speaker, Dr. Janit Veerasinghe. We are incredibly fortunate to have Veerasinghe with us today to share his expertise and insight on advancement in rocket propulsion technology. Before we begin, I am excited to have all of you for taking the time to join us today. Your presence and enthusiasm mean a lot to us, and we are confident that you will leave this session with a great understanding of rocket engines and their future potential. Let's get this started. And once again, welcome to Trust Talk. We hope you enjoy the session.
Thank you, Medini. Now it's time for the moment you all have been waiting for us. It's my great pleasure to introduce Dr. Janit Veerasinghe, a leading expert in rocket systems. Dr. Veerasinghe will now share insights into the power behind rocket engines and how they are enabling the next frontier of human space exploration. Dr. Veerasinghe, over to you.
Thank you very much for the wonderful introduction. Let me share my screen first. Can you see my screen now?
Yes, we can, sir.
Okay. All right. So once again, thank you very much, SETS or USL, for your invitation, and I'm really happy to be here once again. So today we are going to discuss about the mechanism of rockets and also the future of space exploration. Uh, so without any further ado, let's see what we can learn from that. And I especially like about the part of the future of space because I believe the future of space is actually lying between the participants uh, who are looking at this presentation today, because if I ask the question of why you are here, because all of you are uh, fascinated about the space tech, and so that fascination is leading into innovation, and that creates the future. So let's have a look at on how this space tech evolved over the time, and then let's see what would be your contribution into this space tech that comes later in this session. Uh, so let's start with the history of the rockets. Probably this is something you already heard. Um, Rocket technology is something having a really long history. So, uh, especially the solid uh, engines or solid rocket motors, they had been in use for more than um, a millennium. Uh, so, in ancient China, people discovered the recipe for gunpowder, and they use this gunpowder recipe to make ancient rockets, and they use this in their uh, mm, wars, especially with their fights with the nearby Mongol Empire. Uh, Later, the foundations or the modern day rocketry or the mechanisms uh, is led by Sir Isaac Newton. So he's the one who proposed the laws of motion, and then the path for the modern day rocketry came up with uh, the mathematician Konstantin Tsiolkovsky. He is the one actually derived the rocket formula. So I'm not going to explain much about Newton's laws, but because I'm pretty sure that you all aware of that. So basically, in any rocket engine, what you are going to do is uh, you eject a mass out of of a system, and based on how fast you ejecting it, and based on how much mass flow rate or mass you are getting rid of, you can get a thrust in equal opposite direction. So that's the principle of any kind of rocket engine. And there are various types of rockets that using this principle. Um, so I'm going to add one more slide about the modern history of rockets. So modern history, uh, can you still see my slides?
Yes, yes, doctor.
Ah, okay, okay. So in modern history, it started with the research conducted by Robert H. Goddard. He is the father of the liquid propulsion systems, and later Goddard's work has been continued by a German scientist, uh, Werner von Braun. I think you can yeah, see here. And then mm, so Goddard's work started in early 1900s, and uh, later uh, this technology is developed in Germany for the Second World War. And after the Second World War, this technology is transferred into emerging superpowers on those days, the Soviet Union and the United States. So early US and USSR rockets are actually based on the works conducted by Von Braun. Von Braun created um, the world's first ballistic missile, which is known as B-2 rocket. and it is the first time that people used turbopumps um, in liquid propulsion systems. We'll discuss this further in upcoming slides about different types of liquid propulsion systems. Uh, However, after the Second World War, these V2 rockets were transferred into various testing facilities in Soviet Union and United States, and they independently developed their rocket technology. However, the race for the space initially dominated by Soviet Union because the first few milestones of the space race uh, is achieved by Soviet Union. For an example, in 57, they launched the first satellite. Then they successfully managed to send the first living being into space, Laika, in 1957. Then they sent the first human into space. Most of you might know about Yuri Gagarin in 1961. So US also wanted to compete, and they did a massive plan of nearly a decade about how to win this race, and finally they managed to land on moon in 69. So this is a brief history of rockets. So you can see the technology of solid propellants, which is having nearly a millennia of history. And after the introduction of the liquid propulsion systems, all of a sudden there was a huge expand and huge step in the technology, and people even managed to land on moon within about the technology development of 50 years. Uh, anyway, so when we mention a rocket, the first thing comes into our mind is the launching vehicle. Uh, so launching vehicles, the examples are things like Saturn V rocket, um, Ariane rocket, the most recent SpaceX Falcon 9, these kind of rockets. And also we are using rockets in spacecraft as well. So once you reach the orbit, spacecraft itself also having small rocket systems. Uh, Unlike the rocket systems in launching vehicles, these systems consumes comparatively less power, and these are the more exotic one comparing to the conventional uh, chemical rocket systems. However, that doesn't mean chemical systems are going to be obsolete, because in order to get out of the Earth's gravitational well, we need to use conventional systems like solid systems and liquid systems. So several times I talked about solid rockets, liquid rockets. Uh, and so far, I'll go for a proper classification on my next slide. However, these two systems, solid and liquid, are the most common type of propulsion systems that we can see. Uh, so if I explain more about the solid system, uh, so this is the most basic design you can have, and because of that, it's really easy for anyone with right material to fabricate this kind of system. When it comes to liquid rocket, things are getting a little bit complex, but still, so we have a metaphor saying if a technology is highly advanced, we are saying, oh, this is something like this is a rocket technology. But nowadays, even building a liquid system uh, is comparatively easier task than it used to be. So it's I will say that that's not rocket science is less involved in building a liquid rocket as well. Let's have a classification of the current systems that we are using. So we can classify rockets on different types of um, uh, criteria. One is based on the method of propulsion, and this is the most popular type of classification. So as I mentioned earlier, we have chemical rockets. So chemical rockets can be further divided into two types, the solid ones and liquid ones. Then we have electrical systems. Electrical systems mainly using in spacecraft rather than in launching vehicles. And we have some other exotic systems like solar, nuclear, and combination of few of these. Also, we can classify based on the stages. Single stage rockets, these are usually sounding rockets. So most of the cases, we don't have any orbital capabilities using this type of rockets, but you can gather information about the weather data and hobby rockets. These are belongs to this category. Multi-stage rockets. These are the ones we are using for space exploration. And multi-stage can be also divided into two subgroups based on how the stages are positioned. Um, and also, we can classify rockets by their application. Uh, so when we say the word rocket, the first thing comes into our mind is space exploration. But actually, rocket technology is built upon the requirements from military. Early rockets, for an example, V2, is a missile, and later on, the rocket technology is developed for the transportation of nuclear warheads. Uh, I mentioned previously about the rocket development by United States and Soviet Russia, and both of them were actually trying to further enhance the capabilities of V2 rocket into intercontinental ballistic missiles with nuclear capabilities. So that's where the uh, uh, actual technology development started, but later it expanded into space. Other than that, rockets are using in weather uh, observations and also rockets using in aircraft propulsion too. Um, and few examples are given here. And booster rockets. So I think you already know what booster rockets are. These are the uh, um, engines that we use to boost launching vehicles, such as in, space shuttle and retro rockets. Retro rockets, especially using in orbital maneuvers, especially for deorbital maneuvers in various spacecraft and also in space station as well. Mm, so yeah, military rockets we can further divide it into different types of missiles and launching modes and range as well. So so let's move into chemical rockets. So the example given here is a rocket developed by the Rocketry Club of Australian National University. So actually, this rocket is uh, assembled by the undergraduate students of our university. So this kind of chemical rocket we can have either solid propellant or liquid propellant. Uh, and there's another type called hybrid propellant. Um, so there are two terms that are used in this type of devices. We use the term motor if it is a solid rocket, and we use the term engine if it is a liquid rocket. So in solid propellants, as I mentioned earlier, these are really simple, and people used to build this kind of rockets more than for more than thousands of years. And this technology is also extensively using in the military. Uh, and so you can see uh, the configuration is quite simple, and this is the exact configuration you are seeing in uh, uh, those sky trackers that you are using in New Year. Uh, so advantages of this kind of solid propellant is it is compact in size comparing to a liquid rocket. Uh, um, if we are using a liquid propellant, we need to use pumps or some kind of pressure difference to move the propellant from the propellant storage tank into the combustion chamber. But we don't need to do that in solids. And also we have high thrust to weight ratio. So this is a measurement of how powerful our rocket is, and this requires very little maintenance. So because of this fact, solid rockets are again extensively used in military, because in military, time is a critical factor. So you need to prepare your system in very short notice and very short time. And also solid propellants are safe, I mean, comparatively or relatively safe, because liquid propellants, if you are storing, you need special vessels, and also most of the time, uh, unless you are using a hypergolic type of propellant, you are going to have a pressurized system. So it is subjected to leaks, and uh, there is an hazard always associated with this kind of high pressurized system. Um, but that doesn't mean solid systems having disadvantages. The biggest disadvantage is you can't shut it down once it's you ignite it. It's like if you light a firecracker, you can't blow it off. And also you can use it once. Uh, Actually, NASA tried to get rid of this disadvantage by their solid boosters used in space shuttle. They used, so these are the solid boosters that they use. And after their use, those were designed to descend back to Earth using parachutes, and they try to reuse it. And this is the only example that I can find about reusing of solid propellants, solid propelled rocket. But in most of the cases, I'll say more than 90%, uh, you can't reuse solid rockets. So every time you are using a rocket, you need to build a new one. Uh, so that's why people moved on with liquid systems. And this slide gives about the thrust profile on different grain configuration. So let's say you are using standard gunpowder, and depending on how you put your grains, the thrust profile is going to be different. So that's what given in this slide. And there are few different compositions of solid propellants as well. First one is called homogeneous or colloidal propellants. So in here, both fuel and oxidizer containing same molecules which decompose during combustion. I think the most common example I can give is something like nitroglycerin and nitrocellulose. Uh, and also there are another type called composite or heterogeneous propellants. So this is a mixture of oxidizing crystal and powdered fuel held together by a binder. Sometimes light metal powders are also adding to increase the energy of the combustion process and fuel density. These are more stable comparing to these homogeneous ones. And using in long-term rockets, mm, however, these light metals make their exhaust exhaust little bit toxic. There's another type called composite or modified double-based propellants, and these are a heterogeneous combination of double-based homogeneous or colloidal propellants and composite propellants. Uh, now let's move into the liquid system. So in here, we are replacing solid propellant with a liquid propellant. Um, Sometimes people using one type of liquid propellant. We are called this monopropellant type, and we also have bipropellant. That means most of the cases we have oxidizer and uh, we have the propellant separately and the oxidizer separately. So that's how the liquid type of engine is working. And in order to ignite this kind of rocket, we can use chemical, pyrotechnical, or electrical system. So ignition, this is something equivalent to if you are uh, going to use a firecracker, you are going to use a match. This is pretty much the same uh, thing, but happens in chemically or electrically. If it is electrical is the most common one, so you are just um, passing a current through a wire, and the heat of that wire cause the propellant to start the combustion reaction. Um, okay, so in this slide, it gives the advantages and disadvantages of liquid systems. Uh, so advantages, relatively, relatively solid programs, it's a little bit complex, but still it's a simple design comparing to uh, there are more types of uh, propulsion systems coming up. So it's a little bit complex than solid, but still it's a simple design. Uh, it's reliable, but still need some plumbing. And this is extensively used in space exploration. So it's got a big flight heritage. And anytime you can turn these things on and off. Disadvantages are fuels can be toxic. I mean, it can be toxic to environment. It can be toxic to human as well. For an example, some hypergolic programs are really corrosive, but even a general propellant, something like RP1, are harming the environment. And uh, thrust is also somewhat lower, and exhaust speeds are also lower. So because of that, the overall uh, efficiency of the rocket is also low. So again, I use the same uh, photo I used before because space shuttle itself using liquid engine as well. So that's the engine used in this orange tank and also in the engines of the shuttle itself. So how this liquid propulsion system is made? So there are two types of basic configuration. The first one is called pressure fed. So in liquid systems, this is the uh, simpler version, I'll say. So we have just a fuel tank and oxidizer tank. So because of the pressure inside these tanks, it is controlled through this control valve and directly fed into the combustion chamber. So this is the most simpler version, and early V2 rockets, sorry, before V2, uh, for an example, in Goddard's test, this type is used, but in V2, they used a different configuration called this pump-fed system. So in pump-fed system, the fuel and oxidizer, again, similar to the pressure fed, we have it's stored inside the tanks, but pumps are used to mix these together and feeding into the combustion chamber. Uh, this technique is more complex because these are turbo pumps and it requires a bit of uh, advanced technology to be made. Uh, however, so the functions are given here. So it raises the pressure of the propellant and then they are going to be feed into the thrust chambers. Uh, and Previously I told you about in some systems we are just using just one type of propellant called monopropellant. Uh, in monopropellant, unlike bipropellant, you have just one type of liquid and it is passing through a catalyst and the catalyst reaction generates heat and that heat products are going to expelled through a nozzle. For an example, the most common monopropellant is hydrogen peroxide. You might see it in your uh, first aid boxes. Hydrogen peroxide, we can dissociate it into water and oxygen. And Naturally, also this reaction is happening in very slow rates. But if you pass hydrogen peroxide through a catalyst, you can accelerate this reaction. But again, the hydrogen peroxide you can find in your first aid kits are really low in concentration. I think something like 2%. Uh, but for rockets, you need high concentrations of hydrogen peroxide. Biopropellant, I think we kind of discussed everything mentioned in here. Hmm, yeah, so let's move into next slide. Okay, so here's a comparison of bipropellants and most common oxidizer is liquid oxygen. Uh, and there are some other oxidizers as well, something like nitrogen tetroxide or N2O4. Fuel are going to be different depending on the system requirements, but most common fuel is liquid hydrogen. Uh, and RP1 is also a common fuel, I'll say. Rocket propellant 1 or RP1. This is actually a cleaner version of kerosene. Uh, and there are some other types of fuel as well used in different types of space missions. So previously I told when we are having a solid system, the biggest disadvantage of solid is we can't turn it off. So in hybrid system, we are using solid fuel and but this type of system actually you can shut it off and start on like a liquid system. So this is kind of an intermediate uh, version between solid or liquid propulsion system. Most of the time, the fuel is the solid part and oxidizer is the liquid part because the most common oxidizer we have is liquid oxygen. So this is the most common configuration, but you can do the other way as well. Uh, why I emphasizing this hybrid system is if you are planning to build your own propulsion system, this is the type of system that I'm going to suggest. Because once you have liquid oxygen can pretty much burn anything. For an example, uh, in last year I participated to one of the rocketry competition in US, and one university used paraffin wax as solid fuel. So we have paraffin wax uh, based a fuel container, and they are passing liquid oxygen through that, and it uh, it gives a really good performance to their system. Uh, And also, we have another university in here called Monash University. They also developed a similar system using a solid fuel and oxidizer. So uh, this is, I'll say, if you are home building a rocket, this is an easier configuration. There are some more advantages as well. You can easily thrust controls, less constituents, um, and because you can use any type of anything that burns, you have more choices to choose uh, the fuel as well. And also, you can use different types of crane configurations compared to solid uh, type of rocket motor. Mm, okay. Now let's move into electric systems. So previously I was mentioning about chemical systems. These chemical systems mainly using in launching vehicles or the bigger rockets you are seeing. Electric rocket engines, and most of the rocket engines we are going to discuss hereafter are using in spacecraft. So these spacecrafts can be uh, satellites most of the time, and also you can use them in other types of systems. For an example, uh, um, if you need to change the orbits of a space station, people are using these type of propulsion systems. Uh, Interestingly, the electric propulsion idea is also um, old as uh, uh, the liquid propulsion types because the electric propulsion idea is also proposed by Tsiolkovsky in 1911. But it took some time for them to use in actual space missions. Um, the first type of electric systems people used are called iron engine. And to be more specific, these are called gridded iron thrusters. And I think these use cesium compounds in their initial test. Mm, Later, there was so much interest in electric propulsion systems, and various uh, different types of electric propulsion systems were proposed and developed. So this is a uh, classification of different types of electric propulsion. So we can find three different types. Uh, there are some systems that use the electrostatic force, and we can further divide into ion thrusters, um, field emission electric propulsion thrusters or field thrusters, and colloidal propulsion thrusters. And there's another version called electrothermal. That means we are using electricity to heat up the propellant and then using that heated propellant in our rocket. So they can be further divided into resistor jets and arc jets. In electromagnetic, we are using magnetic field forces to accelerate our propulsion medium. And most of these cases, general reactance from uh, from a common reaction of propellants and oxidizers, they produce gases, but in electromagnetic, we need to produce plasma. The reason is gases are not responding to magnetic fields. So we need to have a medium that is responding to magnetic field. So in order to do that, we have to further energize gases. And when we further energize, they are going to dissociate into ions, and this ion and electron mix or a plasma, we can control it using electromagnetic forces. So there are various electromagnetic types, magnetodynamic thrusters, Hall thrusters, pulse plasma thrusters, so and so. Uh, so another advantage of using electric propulsion systems are they are really efficient. So here you can see a comparison of different type of electric propulsion systems on the first three rows: electrothermal, electrostatic, and electromagnetic, and it's compared with a monopropellant system, which is a liquid system. So you can see the force or the thrust is going to be significantly lower comparing to a monopropellant system. But if you consider the efficiency, in here it's given in ISP. ISP stands for specific impulse of a rocket. It's a measurement of how efficient your rocket is. You can see every type of electric propulsion systems is nearly more than 3 times efficient than a conventional monopropellant system. Mm, and another advantage is the burn time. If you're using a conventional type of uh, rocket, like a solid rocket or liquid rocket, the maximum burn time you can achieve is something um, lasting for minutes. Maximum, maybe you can go for hours if you are using a monopropellant system in space or in orbit. Uh, but uh, every type of other electric system, you can burn them for months or years. So for interplanetary missions, uh, electric systems are the only solution remaining uh, compared to the conventional liquid or solid types of systems. Uh, if we consider propellants, uh, monopropellants, you have less uh, propellants to choose comparing to electric systems, but the propellants is highly depending on the type of electric propulsion you are going to use. You can see there are some interesting propellants like Teflon. So Teflon is it's a type of plastic that you can find in non-stick kitchen utensils that can be also used in magnetic propulsion. If I'm going to be more specific, Teflon is using in pulse plasma thrusters, and also these are some noble gases that you can use, and some lighter metals like lithium and hydrogen. Um, okay, let's see each of these different types of electric propulsion systems and how they work. So in electrostatic, we can divide it into ion thrusters, field thrusters, and collider propulsion. So basically, they are using the electrostatic force um, to accelerate uh, ions. So that's the basic principle behind all of these electrostatic systems. Mm, so here I gave a slide about uh, how the energy can be used to ionize a particle, but I'll quickly skip that. Uh, and yeah, these are the ionization potentials of different propellants that we are using in electric propulsion. Uh, you can see uh, most of the cases in noble gases, you can see the ionization potential is somewhat lower, which makes them easier to generate plasma. Uh, but there are some disadvantages comes with the ionization. I mean, ionization potential is not the only uh, factor that deciding when choosing a proper propellant. For an example, krypton considered as a really good candidate for uh, um, ion thrusters, but krypton is expensive. Uh, and because of that factor, people kind of turning into alternating propellants. If I give you a practical example, in initial stages of the Starlink satellites by Elon Musk, SpaceX, the deorbiting maneuver is conducted using Krypton ion engines, but now they turned into argon engines because of the cost. So just one example of how we need to how people using different types of propellant based on the requirement. Okay, so when we go to ion thrusters, so ionization is the physical principle behind this type of thrusters. So if you remember in the last slide, so we energize a particle using electrical energy, and because of that, we can remove electrons out of um, a medium. It can be atoms, it can be molecules, and by after removal, we have a mixture of electrons and ions, and this mixture can be controlled, and we can emit out of our system. So there are two types of discharges you can see in uh, in uh, in standard conditions. So one is called coronal discharge. That means uh, uh, if you have uh, uh, if you have a potential difference and it is with a pointy surface or pointy electrode, you can see this coronal discharge effect. And instead of a pointy surface, if you have two electrodes with a higher potential difference with a blunt electrode, you can get a glow discharge like this. So this is the experiment that we conducted in our laboratory. Uh, you can see how the glow discharge is taken place inside these plates. So if I explain more about this experiment, so this is a, the ground electrode, and the ground electrode is connected into this uh, plate by this circular electrode. Uh, and this is the working electrode. You can see the red wire is coming from the power supply, and in between, so these two electrodes acts as the uh, conducting electrodes, and they are circular shaped in order to create this glow discharge. So in between we have um, two plates or a chamber made of quartz, and inside the chamber we have I'm not sure you can see it probably, but we have a gas line comes out of here, and then it is giving off gas to the inside of this chamber, and from somewhere here, which is hidden, we have the gas exhaust. So once and the gas type we are using here is argon. So I'll play this video. You can see, uh, and so those arc-like things we call it streamers, and there is uniform light, that kind of purplish color, that's the glow discharge. So this is the type of phenomenon that's being used in electrostatic propulsion systems. This gas uh, is acting as the propellant, and and after being converted into the plasma, it can be used to eject from the nozzle, and it gives a thrust force to the system. Mm, okay, so based on that system, this is a iron engine prototype that's been built by my students. This is a mini project of them. Uh, this is called an air breathing iron engine prototype. We call it air breathing because unlike a rocket engine works in space, this is using the atmospheric air to ionize, and this is the high voltage power supply, and it's directed into these tiny needles. Um, and they 3D printed this nozzle, and I'll play this video. So you can see uh, uh, it is giving enough force to uh, have a deflection in this paper. Mm, So the reason why we call it air breathing is it is using the standard atmospheric air. Uh, so, oh, okay, at the end of the video, so what happens here is we cranking up the power into a point that this, uh, I think it will start soon. Uh, Instead of ionizing, an arc is going to take place between the ground electrode and this air over there, and that working electrode. So uh, that's the requirement of using an ion engine. You have to optimize the power which is going into the system to prevent an arc, but still sufficient enough to ionize air and create a thrust. So in space, the difference is we have to carry the gas with us because there's no gas in space. But in low Earth orbit, there's little amount of stray molecule of nitrogen and atomic oxygen, and people are trying to make systems similar to this, which collect these gas molecules and using as a propellant. But again, that is only achievable in uh, low Earth orbit. Again, lower areas of low Earth orbit, I will say. So um, it's an active area of research currently to this type of devices in low Earth orbit. But if you're going beyond low Earth orbit, you have to carry your propellant with you. Mm, if I move to next slide, uh, so this is another type of ion engine. Uh, uh, in here, it's a little bit complex comparing to the previous case. We have so so in here we create the plasma inside the chamber, and we have two grids over here. If you look closely, you can see the first grid is positively charged and the second grid is negatively charged. So what happens is you have a plasma, or you have a mixture of positive and negative ions here. And because of the effect of these grids, especially the positively charged grid, there is an accumulation of charges inside because equal charges going to repel. But after some time, uh, the plasma density is going to get higher and higher, and it's going to overcome this positive grid, and it's going to pass through that grid. But after the positive grid, there is a negative grid. So uh, positive and negative charges, they attract each other. So it is going to accelerate towards this negative grid. But because of the gridded nature, it's going to expel out of the system. And Another design configuration that people used in here is while in use, the system is continuously using positive ions, and there is a potential that the whole system going to charge uh, negatively because you are getting rid of positive ions. And what happens is these positively charged ions might come back to the system because, again, positive and negative, they attract each other. So in order to get rid of that, we are using a hollow cathode like this. So it continuously emits electrons into this ion stream and neutralizing this charge. So that's how an ion thruster is work in space. Mm, So these are various types of propellants used in ion thrusters. As I mentioned earlier, uh, noble gases are mm, a very popular choice. But again, krypton and xenon are a little bit exotic and rare to find. So people shifting into things like argon. Um, Radon, people don't use it because of the radioactive behavior, but still it can be used. Helium and neon can be used, but the problem is uh, in helium, the atomic mass is lower. Um, Neon is a good choice. It's kind of giving intermediate efficiency compared to helium and argon. So people trying to use argon, experimental area is use argon, but currently most of the electric systems are relying on either krypton or xenon. So electrothermal. Uh, so as the name mentioned, we are using electricity to heat up a material. If we pass uh, electricity through a conductor, what happens is the conductor is going to heat up. And that heat is used to heat up a propellant and uh, emit through a nozzle. So that's the basic idea of a resistor jet type rockets. Uh, And there are different configurations as well by using different type of heating elements in different configurations to achieve this thrust. Resistor jets are really simple device, and there's another type called arc jet. So arc jet is somewhat similar to how plasma works. We have uh, a cathode and anode, and we are sending an electric spark between them. And that spark generate heats, and it can accelerate uh, gases. And oh, uh, can you see my video?
No, sir. I think you haven't switched on your video.
Okay.
Okay. We can see you now, sir. Thank you.
Okay. Let me. Hmm. Okay. I'm not sure you can see this properly.
We are unable to see the
Uh,
entire thing.
okay. Uh, uh, I think Zoom is not giving. Okay. Anyway, let's leave that. Anyway, this is a small prototype of an object. So it is having the similar configuration, but anyway, Zoom is not letting me do. Uh, Maybe I'll try it again. Can no, it's kind of vanishing, right?
Yes, sir.
Uh, okay.
I think it's because of
Anyway,
the virtual wallpaper.
okay. By assuming that even not now, okay. Uh, Anyway, I'll explain what it is. So this is something similar to that. So we have a power supply, and there is a gas inlet, but you can't see the cathode and anode. But I'm going to remove the part, so you will able to see the actual cathode inside. Uh, Sorry about the disturbance comes from the Zoom, but so this is the cathode
Excuse me,
part.
sir.
Yeah.
You can try removing the background. I think that might work.
Okay. Let me try. Hmm. think it's not letting me to do that. Uh, can you see my slides again?
Yes, sir, we can see your slides.
Oh, okay. Yeah, sorry about that. Uh, yeah, it's not letting me to remove the thing. Maybe I'll post up the photo as this one.
Okay, sir.
Uh, anyway, that's how an object works. Uh, okay, and okay, the remaining one is electromagnetic. So here we are using magnetic fields to accelerate plasma. The most common type that people are researching at the moment is this magnetodynamic plasma type. Uh, and Hall thrusters and pulse plasma thrusters are extensively using already in different types of space missions. Um, but this is going to be the future. So, for an example, if you need to travel to Mars in a manned mission, this type of system might be ideal to reach uh, such interplanetary journey in really short uh, time, and also saving lots of uh, food comparing to a conventional system. Uh, so this is a really early version of plasma thrusters using in I think in 1970s. Uh, and pulse plasma thrusters is again a simple design. All you have is similar to the arc jet. You have a anode and cathode. You just give a high voltage, and because of that high voltage and the spark, it's going to convert your propellant into a plasma, and that plasma is emitted through the nozzle. Mm, and there are different types of fuel or propellants used in this type of devices. Here it mentioned Teflon, but other than Teflon, there are so many alternative propellants you can use. And it's simple. That's the main advantage of pulse plasma thruster. But main disadvantage is the amount of thrust you can get is really small. It's in not even, I mean, there are some systems that have millinewton range, but most of the cases it's uh, lower than millinewton range in micronewton, I will say. Mm, and so this is called magnetodynamic plasma thruster, so MPDT. Uh, Comparing to pulse plasma thrusters, you have an external electromagnetic field in these kind of devices. These are efficient, but the biggest issue is this outer magnet. This is an electromagnet. This consumes a lots of power, lots of power, and so and also because of this electromagnet, it is responsible for uh, more than 70% of the total mass of this thruster. Uh, so the thrust to weight ratio is lower, but still people actively uh, engaged on improving this type of thruster. One one type of one configuration proposed is using superconductors to generate this magnetic field instead of standard uh, electromagnet. But yeah, but still, this type of MPDT thrusters are going to be the future of electric propulsion because they have um, relatively more thrust comparing to other plasma thrusters. And there's another type called Hall effect thruster. If you remember the Hall effect you learned in your probably in your physics classes. So imagine this is a conductor and you are passing a current along there with the magnetic field in Z axis. Uh, so if you have this configuration, you are going to observe a Hall voltage in this system. So in Hall effect thruster, similar uh, mechanism is using. So we have a center magnetic field and a magnetic coil around that, and we have a cathode located outside. So this cathode is going to send electrons into the system, and because of the Hall effects, these electrons going through a circular motion inside the thruster. Meanwhile, the propellant is pumped into the system, and because of the motion of these electrons, the propellant is energized, or else I'll say the electron movement rips electrons apart from the propellant molecules or atoms and create a plasma. Um, and that plasma is uh, emitted out of the nozzle due to the Lorentzian forces. So that's the concept of Hall effect thruster. And again, this is developed by Soviets and widely used even now. But there are some not limitations. There are some issues with Hall thrusters as well. Even though we use it, we can't properly model these kind of Hall effect thrusters. Uh, for an example, if with the physics we know, we can calculate how much current is passing between this cathode and anode. But the calculated values are usually larger. The experimental values are usually larger than the calculated value. And we call this an anomalous electric current. And we are not sure yet about what actually caused that phenomenon. And also, it's a little bit tricky to model this kind of Hall effect cluster. So again, a really active area of research uh, to modify and increase efficiency of these kind of Hall effect devices. Uh, and yeah, this is a early type Hall effect thruster used in 70s by Soviet Union. And Hall effect thrusters are going to be used in the proposed lunar gateway. Um, in next decade, we are going to have a space station around Moon, and that space station is going to propelled by this Hall effect thrusters. Mm, and the next type of propulsion is nuclear propulsion. Again, this is a type of propulsion system uh, used in two superpowers during the Cold War era. Both United States and Soviet Union did extensive research on making a nuclear rocket engine. The main target they were after is having nuclear capable bombers which can airborne for extended duration. Extended duration means not in hours but in days and months. So that's why both of these countries worked on this type of devices. And in nuclear propulsion, there are three uh, types of energy release that we are focusing on. One is called fission energy. Uh, we are pretty bad on this because we can create this, but we can't control this. Fusion, we are somewhat good at this, and radioactive isotope decay. So I'll say this is the least uh, uh, risky way of making nuclear propulsion. Uh, so in nuclear propulsion, there's one type. I mean, there are a few types. of nuclear thermal rockets, nuclear rockets. We have nuclear thermal propulsion, nuclear electric propulsion, dual mode, which is a mixture of both of them, and pulse nuclear thermal propulsion. This is a proposed thing and more like a, I'll say, uh, it's more closer to a science fiction rather than uh, building an actual prototype. Uh, in a nuclear thermal, basically what happens is we are using the heat generated in a nuclear core to expand a gas. Advantage of this is uh, once you have this kind of device, you can use any type of gas as a propellant. In here, here they use hydrogen because hydrogen is more common in universe. But in theory, you can use any kind of gas because in any gas, if you heat it, it's going to expand. Um, this is a type of nuclear engine that was developed in 1960s. Uh, so these are the advantages of nuclear propulsion. You can have really high efficiencies, really high thrust values, uh, and you can use any gas as the propellant. Uh, this is another concept uh, called nuclear electric propulsion. So what happens here is similar to the previous case. We have a nuclear power plant, but in here, this nuclear power plant, it's generating electricity, and that electricity is used to drive an electric uh, rocket system. Um, in dual mode propulsion, you have both of them. You have nuclear electric and nuclear thermal mode. In the last type, we called it pulse detonation type. This is more like a concept thing. So we have what we are doing is we are making a controlled nuclear explosions to accelerate a spacecraft into really high velocities. If you are a fan of three-body problem, this is the type of spacecraft they use. If you haven't seen the TV series, I encourage you to have a look. But the thing is, people actually try to create such device, but it cost a lot of money. There was a project called Project Minimac Orion, and uh, but that project is stopped due to financial reasons. And pretty much most all of these nuclear propulsion projects are no longer in use, I'll say, because after the end of this Cold War, people gave up the idea of building nuclear nuclear powered rocket engines. But yeah, this is just a comparison of what USA and Soviet Union done. So US built this Nava system, and Soviet Union built this RD-410 engine. Um I think Soviet Union managed to test fly this as well. They have few nuclear powered uh, satellites in orbit even now. Uh, USA, I'm not sure, but they managed to test these systems, but not in space. That's what I know, uh, and that could be different because most of these are heavily well, how I will say this. And so these kind of projects have a really big, having a really big military interest. So most of these information are classified, so we don't know actually what they have done. This is what is available publicly so far. Um, but other than nuclear rockets, we are using nuclear power, not to propel, but to power several spacecrafts and rovers. For an example, Curiosity rover using radioisotopic thermoelectric generator or RTGs to power it up, and this is working for more than 10 years now. And if you have a look at the Curiosity rover, this is the RTG unit located behind. So these small wing-like things are the radiators that used to get rid of the excessive heat. And this is a plutonium powered one. And you might heard about Voyager 1 and 2 since 1977. These are still working uh, closer to 50 years. And Voyager also having this kind of RTG to power up its electronic system because it's too far away from sun to use solar panels to generate electricity. Uh, uh, okay, one more concept. This is called propulsion, and in beam propulsion, there are some rocket uh, engines that use the same concept. So in beam propulsion, basically, what happens is we are using uh, laser, microwave, or light to propel a spacecraft so in beam propelled spacecraft, there's one type called solar rocket engine. What it does is this is similar to a solar concentrator. So we concentrate sunlight into um, a heat receiver, and that heat it is used to expand uh, our propellant. And this case also, hydrogen is the proposed propellant because it's abundance uh, and it's cheaper. Uh, so this is a concept used for solar rocket engines. And yeah, there's another type which use microwave or laser beam projected from somewhere else and directed on a spacecraft similar to this concept that is kind of sharing the same concept to this solar concentrated rocket engine. Uh, so I think I pretty much covered the available rocket engines. So let's move into the second part of this uh, talk or this lecture. Uh, so, as I mentioned earlier, the future of space, uh, I think you are going to share it because you are, I believe most of the parts not here are undergraduate students of Open University of Sri Lanka. So, uh, the future of space and the technology development of this uh, space application is something that you are going to carry and you are going to be the future. So, and one thing I understand is uh, your organization, SEDS, uh, and other organizations, they are doing a really good job on uh, putting all these space enthusiasts and people who are interested in space. You are doing a really good job on keeping them together and doing joint um, projects. But one thing I notice is most of these organizations are only uh, focused on sky observations. It's a good thing to do, but sky observation and having few telescopes and looking at the sky is just one part of this whole astronomy and space technology. If you are planning to move into space technology, there is a new emerging space economy, and there are more opportunities. So I just want to give you an inspiration of what we are doing in Australian National University. Maybe this will give you an idea about how you can get involved in this space tech. I know the biggest drawback or biggest challenge you are having is getting sufficient funds. But now more and more people are getting into space and the technology is getting cheaper. And also there are ways that you can raise funds for you with these kind of research projects uh, that helps to enhance the technology. Plus, they help to enhance your career if you're planning to uh, have or do something related to space. So this is just an inspiration, my next slides. But if you need more help or if you need more advice, just contact me for more information. I would be more than happy to help you. So in Australian National University, we have an undergraduate organization called ANU Rocketry. So what ANU Rocketry does is we build rockets. So basically in Australia, uh, uh, if you are uh, launching rockets as a hobby, you need to get qualified. So there are different types of rocket motors that you can buy. So rocket motors, which means solid engines, solid motors you can buy. And these are divided into these kind of classes. You have micro, low power, mid power, and high power. And you can purchase this. Um, these rocket motors are basically firecrackers. So you have, if you remember my previous slide, it's just a mixture of gunpowder. And if you have a look at YouTube, you can see people even use sugar uh, as a propeller. And this is something you can try. And so this is how a basic, a simple rocket wheel looks like. You have the rocket motor in here, some kind of avionic, and a recovery device. But uh, I don't know the legal status in Sri Lanka, but in Australia, you need to get a license to go for high power rocketry. For an example, this is a level 3 rocket motor that I'm having in my hand. And this kind of rocket motor, it can lift a rocket up to about and this specific motor, it has a range of about 10,000 meter, 10,000 feet. But L3, this can go all the way up to 30,000 feet. So hobby rocketry is something maybe you can also focus on. And inside this payload, I will show you. So these payloads are also developed by our undergrad students. So these payload usually they have a basic things like there's a GPS to recover. Um, Sometimes we are conducting small experiments up in the air, such as air quality measurement, something like that. And there's a control unit, a microcontroller or flight computer. Uh, um, and those who involved in electronics, they know better than me about these type of devices. Most of the times, uh, people use microcontrollers such as Raspberry Pi Pico, um, and to get the data out of that, people use um, radio communication electronic devices like LoRa. Uh, and also, this is an aerobrake system which helps to control the rocket up in the air, and this is still under development. Uh, and so this is a flight data system. And again, all these slides, these are the equipments developed by our undergrad students. Uh, so uh, this case is 3D printed using ABS. And so this flight data system, this is like a portable computer or a field computer. And the main uh, 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 controlling system or the computer system here is Banana Pi. You might heard about Raspberry Pi. So Banana Pi is the Chinese version of that. So that is the heart of this flight data system. Um, and this is using to get data from the rocket, I mean, various parameters like the GPS location, velocity, etc. And this software system is called Rerun IO. It's an integrated system that can display data such as GPS, acceleration, those kind of data in a graphical interface like this. So you can easily integrate this into this system. Uh, and yeah, this is a GPS recovery system. So the battery is attached to this GPS, and this is homemade uh, the recovery gear, and this is running Arduino. So it's giving you the coordinates. And this is a radio data link. And here people using RTL SDR. And this is a really cheap radio interface you can buy. If I turned on my camera again, I'm not sure you can see it. Yeah. So this is this is the cheapest RTL SDR you can buy that I have. This is about $10-15, I'll say. This is the uh, in here also we are using something similar but little expensive, but you can go with this kind of cheaper SDR as well. And this is the antenna. Again, it's a homemade antenna that we use to get this radio link, which share the information of our rocketry system to the computer. Uh, Okay, so those are about the solid systems that our undergrad students are building, and this is kind of our future project. We are also involved in making a liquid propulsion system. In this one, we use our oxidizer is liquid oxygen. Uh, our uh, propellant or our fuel is ethanol. So, so this tank, this is the ethanol system, and this is the oxygen system. And we 3D printed this nozzle as well using stainless steel. This has been, uh, I mean, this is um, this project we are planning to execute in, I don't know, 3-4 years from now, because still we are testing the system. But yeah, this is the future plans of the aerial rocketry. Uh, so my suggestion to you is maybe you can also get an inspiration for these projects, and maybe you can try to develop your own technology as well. It's not going to help the technology development of Sri Lanka, but it's also benefit you as well. So just a thought, and let me know if you need any further help. I'm more than happy to give any help for your organization. And just before one more. So this is the thrust measuring system of our liquid engine. So we mount the rocket engine part here, and I'm not sure it's clear, but there's a lever system. So when it pushes this up, this lever type of thing going down, and that thrust is measured by using this load cell. Load cell is an electronic device that converts thrust force into an electrical signal, so we can measure how much thrust is it going to develop. And yeah, so as I mentioned, just reach out to me if you going to have such a plan, because that's something that will rise our country, our nation into a new era. And it's up to you to develop this technology, because nobody is going to give this for free unless you are going to develop it by yourself. And uh, another two slides before I conclude today's lecture. So again, today the participants that we have here are, I guess most of you are undergraduate students, and some of you might be in your uh, closer to the end of your undergrad career and planning to move in academic pathway. So if you like to proceed in academic pathway, you might be looking into higher studies abroad. So my suggestion is get your English qualification, go for IELTS or TOEFL, straight up your research qualification and decide when to apply. So if you have any interest in studying Australia, this is where I did my PhD, Queensland University of Technology, and I have given the link. So this is the page that will give you information about the current PhD projects. So if you're planning to go for a PhD or for MPhil in Australia, this is one place that you can look, and this is where I got my PhD from. So you can try if you plan to do your higher studies in Australia. And also, I should mention, sorry, uh, uh, I should mention the page of Australian National University as well. This is uh, and this is the page of School of Engineering. Uh, oh, sorry, it's not where I was planning to be. I think, okay. So what is it? Okay, for some reason that slide is changing. What's wrong with that? Okay, I'm sorry about this, but uh, I will uh, uh, I will share these slides with you because the next slide is having the link to the uh, school page of Australian National University where I currently work. This is where you can find similar type of opportunities for PhDs and masters by research in NU, Australian National University. And this is the page for engineering. And you can also do the same thing in our School of Science as well, especially if you are interested on other topics in astronomy. For an example, like astrophysics, gravitational waves, um, uh, even electric propulsion, they have similar projects to ours. Unfortunately, for some reason, I can't go into that slide, but yeah, I will share you the links for both Australian National University and uh, Queensland University of Technology. So thank you very much. And before I finish, these are some milestones I would like to share. I had an opportunity to visit White Sand Missile Base in US, where they keep one of the smuggled V2 rocket in their base. They modified this V2 rocket after Second World War, and they used this for their research, and later they developed, if you remember the space history, they built a redstone missile based on this technology. And also I had the opportunity to visit NASA Houston and have a look at the two main launching systems. This is Saturn V rocket, and this is SpaceX booster, which is in display in NASA Houston. And also, I had an opportunity to meet Jamila Gilbert. She's an astronaut from Virgin Galactic. So, thank you very much for your patience and your attendance. Wish you all the best. And yeah, if you have any questions, I'm happy to answer. Thank you.
Uh, Thank you so much, Dr. Veer Singha, for that very enlightening and very inspiring presentation. Now it's time for our question and answer session. So, dear audience, if you have any questions, please drop them in the chat and we will try to get through as many as we can. And also, please feel free to raise your hand to speak directly. Um, Dr. Virsinger, we actually have a question on the chat. So it says, what new materials are being used in modern rocket engines to withstand higher pressure and temperatures?
The simplest answer is alloys. So it's going to be, I mean, even if you have a look at on traditional material like stainless steel, maybe it's an alloy, but we are trying, we are trying to mix with different types of metals and different ratios. So that's the simplest answer I can give. And in research, right, for an example, even us, we are trying to integrate nanomaterials. Uh, but the integration of nanomaterials is not directly related into chemical types of chemical rocket engines, but for electric engines. The reason is, remember that I told we can use electric engines for hours or days. uh, so during this process, uh, the material which makes the inner walls of these channels are going to degrade. It's not like a corrosion, but what happens is the plasma interact with the material and it removes the atoms out of it. So it's something similar to corrosion, but corrosion involves oxidation. But this is not like corrosion, but still it is removing the materials out of it. So we are trying to remedy that situation. Actually, it's something really hard. um, another type of materials that we trying to use and already in use are ceramics. Uh, Examples are something like boron nitride, silicon carbide. But problem with them is those are tricky to handle because if we have a metal, you can easily heat it up, you can mold it to any shape. But if you have something like if you have a ceramic, you can't do that. I mean, mm, heat treatment is not going to work. So the technique we are using is called hot pressing. So it's like you press them together in high heat. But that's not easy as molding a metal. We try to, I mean, we are trying to integrate nanomaterials. And also we are trying with different shapes that is going to have least interaction with these plasma. So yeah, those are the things I can that comes into my mind right now. Yeah. Meanwhile, I will because I had that small issue with the slides. I'm going to post the two links into the chat box. So if you're planning to study abroad, not abroad, in either ANU or QUT, just you can just use these links.
Thank you very much, sir, for being so considerate. So do we have, okay, we have another question which says, will the development of nuclear propulsion technologies replace current propulsion systems?
That's a tricky question. The reason is uh, previously, I mean, about uh, during the Cold War period, the two superpowers are rushing into research and development of nuclear propulsion. But now, nuclear technology is heavily regulated. Uh, so, because of that reason, it's a little bit tricky to work on such systems. Uh, I will say uh, nuclear thermal might be an option, but I mean, this is just my personal opinion. Still, it will take at least 50 years, I guess, because now the current trend is towards electrical comparing to nuclear. But down down this road, there will be a time that the electricity we are going to generate from solar is not going to be sufficient. At that stage, I think people will move into nuclear electrical systems. But so far, most of the space exploration lies before the orbit of, I'll say, Mars. And because of that, we have plenty of sunlight to generate electricity, and the efficiency of our solar power generation techniques, I mean, the solar cells are also increasing. Previously, people were using silicon type of solar cell, but now people using a different type of solar cell called multi-junction solar cells. So you can harvest energy from all the different areas or different, I'll say, wavelengths of the solar spectrum, and these are really efficient. But once people reach beyond the maybe I don't know uh, when people need to reach beyond the orbit of Mars or Jupiter, I think solar power is not going to give us sufficient energy, and at that state, maybe we have to shift to nuclear power. So the current, uh, but currently, there's not, I'll say, yeah, I don't see much trend in nuclear propulsion because of this regulation, but it will get changed. Yeah.
Thank you, sir, and thank you for the question, Kalinga. We have another question. How can students like
Ah,
us get involved in rocket engine research?
um, Uh, well, you have I think you already achieved the first step. You have a good organization, and you organize yourself who are having similar interests. So the next step is building your own engine. So that's why I mentioned about the regulations previously. Uh, in Australia, it's heavily regulated. For an example, in my state, we can't assemble our own uh, solid motor. I'm staying in Australian Capital Territories, and we are not allowed to make it. So we have to buy it. But I don't know the exact legal state, but I think it's much easier in Sri Lanka compared to here. So if you are going for a solid engine, I mean, if you have a look at uh, other sources, um, for an example, in YouTube, you can see plenty of tutorials and homemade engines. I think that's the starting point. But the thing is, building a rocket is highly multidisciplinary. The rocket motor, or the propulsion we are going to talk about, is just one part. Other than that, you need avionics, recovery, uh, aerodynamics, and structural. So you have to put all these uh, um, disciplines together. So that's the advantage of having a big team. So if you have people interested in software engineering, they can develop the codes that we need to control the avionics and get the data. And if you have people interested in material science, they can be allocated into materials design um, and shapes. If you have people, I mean, I believe majority of the participants today are interested in propulsion, so they can work on the motor. Uh, yeah, and also this is something totally different. But let's say you have students who involved in commerce or business. Actually, they are the one who brings the money. For an example, if you can, mm, I mean, a really simple project, what I can think of, which brings money, is you can send an high altitude balloon with a sponsor's logo. You can do the same in a test rocket as well. Um, so you can combine all these different expertise together, and you can start. And I believe, even if you reach, I mean, uh, what I'm thinking is, if you reach the admin or the uh, academic staff, they might help you as well, because this is something university students doing throughout the world. And also there are some competitions that use money. Uh, so I think you already have the uh, first step. You have the uh, background at the moment because you have a proper organization, and the next step is just planning and execute. That's that's my what my opinion is. And there are so many experts out there, and I'm pretty sure, I mean, even if they are located outside Sri Lanka, I'm pretty sure anyone will help you, including me.
Yes, sir. Thank you, sir. And yes, teamwork is definitely key, I guess. And thank you so much, sir, for your very invaluable ideas. Do we have any more questions from our audience? Um, okay, we have one more question, sir. Do you think SpaceX will catch the super heavy booster tomorrow?
Okay. Um, there are some questions that I don't have an answer.
Coming from
Um,
Kalika
let's
Dhananjay.
hope so. Um, I don't know, to be honest. Anything else?
Um, do we have any more questions?
Okay, I think maybe we can conclude. And yeah,
Yeah.
I put, okay, I'll put my email address also. If anyone is shy to answer, shy to put any question, or if someone needs to contact me, I will just put my email in the chat box. So you can send me a direct email if you like.
Thank you so much,
Um,
sir. Yes, and since we have no further questions, let's move forward with the night's proceedings. Thank you so much, sir, once again. And Sharindu, over to you.
I would like to give our tribute to our guest speaker, Dr. Veera Singh. Sir, please accept this. We are truly grateful to Dr. Janit Veerasinghe for sharing such a wealth of knowledge with us today. It's not every day that we got to hear directly from an expert in the field about the incredible technology that will one day take us to the stars. As we near the end of our webinar, it's time to express our gratitude to all those who made this event possible. I would like to invite the manager of Rocketry Division of SEDS OUSL, Pradeep Kumara, to deliver a vote of thanks on behalf of everyone.
Okay. Uh, as we conclude the talk, I would like to take this opportunity to express my deepest gratitude to everyone who made this event a success. First, a big thank to you, Dr. Our distinguished speaker, Dr. Janit Veerasinghe. Your presentation has provided us with invaluable insight into cutting-edge advancement in rocket propulsion and space exploration. Your knowledge and expertise have inspired us all, and we are truly honored to have had you lead this session. Next, my heartfelt thanks to all the members of SETS USL who contribute in various ways to the success of this webinar. For behind the scenes effort to direction involvement, every contribution played a crucial role in making this event a reality. Additionally, I would like to express my sincere thanks to the media division for their outstanding work on the promotional materials, including the flyers and videos. Your creativity and support we vital in bringing this webinar to life and ensure it reach a wide audience. And finally, to all the participants who join us today, thank you. Your engagement and enthusiasm have made this webinar a great success, and we hope you found it both informative and inspiring. Please don't forget the fill out feedback form, as your thoughts and suggestions will help us continue, improve, and delivering impactful events in the future. Thank you once again, and we look forward to seeing you at future SETS or USL events. Thank you.
Thank you for that. So, ladies and gentlemen, let's capture this moment forever. Please turn on your cameras, everyone. Let's smile big and make this memory to last a lifetime. Thank you all. So, as we close tonight's webinar, let's take a moment to reflect on what we've learned. The future of space exploration is full of possibilities, and rocket engines will be central to unlocking them. We are living in a remarkable time with technologies that will shape the course of humanity's journey into the cosmos. Thank you again for joining us today. And before we wrap up, don't forget to check out the feedback form we have shared in the chat box. Your input is invaluable to us. We hope you enjoyed Thrust Talk, rocket engines and their powering of the future. Have a great night, and we look very forward to seeing you at our next event. Thank you.